This is the third video in a little series about the exponential function, kind of the foundations of it. How do we develop it? So in the first video, I showed that there exists a function that is equal to its own derivative for every real number, and the other property this function have is that the y-intercept is 1. In the second video, we showed that there's only one such function that has those two properties, that it's equal to its own derivative and that its y-intercept is 1. So what we're going to do, we called that function e in those videos. Hopefully you've watched those, otherwise this video will make very little sense. So we're going to call that function capital E, again, whose domain is the real numbers to the real numbers, and whose codomain is the real numbers, is what I meant, that satisfies these two properties that I just talked about. We're going to call that the exponential function. Surprise. And what we're also going to do is we're going to define the number little e that we've probably seen before. It's going to be the value of my function capital E at 1. And we're going to call it Euler's number. Now maybe you've seen how little e is defined in terms of some kind of a sequence, like the limit as n goes to infinity of 1 plus 1 over n, all raised to the nth power. Yes, that's the same e that I'm talking about here. I'm just not thinking about e in that way right now. I'm telling you a different way to think about e. Remember, I have to do this way. All right, so let's take a little note. Like, what are we doing this for? What's the point of this section? The point of this section is we're trying to build up maybe a lot of what we might take for granted in maybe in our typical education. So what do I mean by that? We're probably comfortable with all the exponent rules and stuff that we get to use for rational exponents. Like, how do you square something? Well, I know that just means you multiply it by itself. I understand what those exponent rules mean, and I understand how do I do x squared times x cubed? Oh, I just add those exponents. We take all those for granted. And so what does it mean, though, to take x to the pi power times x to the square root of 2 power? If I multiply those, do I still add the exponents? How do I know that I still have all those great exponent rules whenever my exponents are, say, arbitrary real numbers instead of rational numbers? And so in other words, what I'm trying to say is we've kind of been playing with this function f whose domain is the rational numbers. We're pretty comfortable with it. And I could think about, I know what it means to take some number e and raise it to the rth power for any rational number q. But again, how do I make sure that it's a well-defined idea in order to take e to, say, the pi power, right? Maybe some irrational number. In particular, though, just some arbitrary real number. How do I know that that makes sense? So what is this function capital E supposed to do? Oh, I'm getting a little bit ahead of myself. So again, back to this. I know that little f here, whose domain is the rational numbers, that it follows the typical exponent rules that we're used to. So for every rational number q and another rational number s, when I plug in r plus s into this function, I know that's e to the r plus s, and I've got exponent rules when these are rational that I just take for granted because I have passed college algebra somehow, and I know that this should be equal to f of r times f of s. So how do I know I can extend this concept again whenever r and s here are any real number, not just rational numbers? So the idea, what's kind of the point of this section, is this function capital E is sort of the bridge to extend this to arbitrary real exponents. So in particular, capital E is sort of the extension of this function little f, so that its domain is not just going to be q. Now we're going to extend that function to all the real numbers. So I hope that you see kind of the difference here. The domain of f is q, whereas the domain of capital E is r. What we're going to show, though, is that e does the exact same thing that this little f I referred to here does for every rational number. And that's, again, what it means for a function to extend another one to perhaps a larger domain. So that's the goal of this video. Sounds like it might be kind of a long video, so I hope you're comfortable. So here's our results here. So the function capital E satisfies the following. It's never ever 0, so it doesn't have any x-intercepts. It's got this pretty cool exponent rule from which we could derive the rest. But then the last thing here is kind of what I was touching on above. E of r for any rational number is just little e to the rth power. And so in particular, this does the same thing as the exponential rules that I know and love. And what I'm doing is I'm just saying capital E is going to give me a way to make sense of something like, e to the square root of 2. It's a function that'll spit that out as a value. So it must be well-defined. It must be a well-defined concept. All right, so here's our proof. So we're going to start just trying to prove each one of these one at a time. So number one, how do I know that this function e is non-zero? Well, that sounds like maybe we could do a contradiction proof. Suppose it is 0 somewhere. Say it's 0 at alpha. And let's let j then be the closed interval whose endpoints are 0 and alpha. Again, I'm not trying to say alpha's to the right of 0. I'm just saying it's an interval that's closed. Its endpoints are these two. Maybe alpha's to the left. Who knows? Well, e is continuous on this interval, so therefore it's bounded on this interval. This probably seems pretty similar familiar in the second video that you watch. So I know that there exists some positive number k that is bigger than or equal to the absolute value of e of x for every single x in my domain. Okay, so by Taylor's theorem, here's what we get. For each natural number n, there exists some number cn that's in this interval j, such that, well, my function e of x is equal to, and what I'm doing is I'm just writing down what's the Taylor polynomial expanded at alpha, at this number alpha, for my function e of x, where again x is some number that's in my interval j as well. So again, this is all just the Taylor polynomial expanded at alpha, and remember the glory of Taylor's theorem is that, well, this polynomial is legit equal to my function, and this kind of factor at the end, the remainder, helps to make that all come true. So Taylor's theorem guarantees that this remainder makes this equality work out. Okay. And so what we're going to do is we're going to think about, well, what do I know about e of alpha? What was the assumption on e of alpha here? Well, e of alpha is 0. That's the assumption here. And since e is the same thing as all of its derivative, guess what? All of these pieces here are 0 as well. So 1, which is e of 0, so I'll do that in a second, is equal to, in this case, I'm just expanding, I'm plugging in 0 for x. I hope that you see that. And so when I plug in 0 for x, that's like where this minus alpha is coming from. And now I'm going to do my little trick that I just noticed, that, hey, by assumption, every single one of these here is 0. And so what do I get? I get that 1 is just equal to this last term at the end, that remainder term from Taylor's theorem. So 1 is equal to that. That's our recap here. Now we're going to do, well, 1, since 1's positive, well, then the absolute value of the right side has to be 1. And so now what we're going to do is we're going to think about, what do I know about e again and its nth derivative? Well, since e to the n is the same thing as e, I know that it's bounded. So I know that that's less than or equal to this k. Remember this k? What's from up here? So again, that comes from the fact that the nth derivative of e is the same thing as e, and we know that. So in particular, let's take the limit of both sides, right? If 1 is less than or equal to this for every n, well then the limit of the left side, the limit of 1 as n goes to infinity, should be less than or equal to this limit over here. And we've seen this before. You know, the limit is as n goes to infinity, so this factorial, n factorial, is definitely going to beat this exponent n. The factorial gets bigger way faster. So what does this say? If the limit of 1 is less than or equal to this limit, that says that 1 is less than or equal to 0, which is of course a contradiction. So we've got our contradiction. Therefore, this exponential, as we're going to call it, e of x, is non-zero for every real number. All right, so we just proved number 1. Let's go back. Number 2, we want to show that this function e kind of has this cool exponent rule that I like. And so if I start doing that now, so number 2, we're going to fix a real number y. So by the above, we just showed that, yeah, for sure, e of y is non-zero. What that's going to allow me to do is to get a little crafty here. I'm going to define a new function g by the following. G of x is equal to e of x plus y over e of y for every real number x. So g is a function of x, so e of y is just a constant. Remember that. I fixed y ahead of time. I'm not saying y is special. I'm just saying it's picked out ahead of time to define this function g. So let's notice a few things about g. What happens when you take its derivative? So when you take the derivative of g, and here's the formula for g, well, e of y down here, don't let it scare you. You don't need a quotient rule. E of y is constant, right? X is the variable. So that should just be e prime of x plus y times e of y. And of course, if you're thinking, what about the chain rule? Well, the derivative of the inside is just 1. Since x is the variable again. And so e prime of x plus y, what do I know about e and e prime? Oh, they're the same function. That's what I know. So this is equal to e of x plus y over e of y. And of course, well, this is exactly what I defined g of x to be. So what have I got? Recap, g prime is g. So g is its own derivative. That's crazy. Let's notice one more thing about g. G of 0, what happens when you plug 0 into this function here? Well, you're plugging 0 in for x. So that would look like e of 0 plus y over e of y, which of course simplifies to 1. So let's recap. We just found out that g is its own derivative and its y-intercept is 1. Now, we had a video that said, well, there's only one function whose its own derivative and whose y-intercept is 1. And we've been calling that function e. Therefore, e is the same thing as g, right? E is the unique function that satisfies these two properties here. So e has to be g. And here's where you're going to see maybe why this goofy looking function, what's the point of it? Well, if g is equal to e here, Well, what's the formula for g? That says e of x plus y over e of y is equal to e of x. Now just multiply that denominator onto the other side, and that's the exponent rule that we know and love. E of x plus y is equal to e of x times e of y. Number 3. What is number 3? I'll go back up. Sorry, for motion sick, I apologize. We want to show that e of r is equal to Euler's number raised to the rth power for every rational number. So let's go back down and try to do that now. So what we're going to do first is show by induction that e of n times x, where n is a natural number, is equal to e of x to the nth power. So induction's fun. Let's do it. Base case, n equals 1. Well, e of 1 times x, that's e of x. And that's the same thing as if I take this number e of x and raise it to the first power. Therefore, yes, this is true when n equals 1. So I'll put a little check mark there. It means it's good. All right, so let's do the inductive hypothesis. Suppose that e of k times x is equal to e of x to the kth power, just for some natural number. What we want to do is show that this is true whenever I plug in k plus 1 instead of k. So what happens when I do that? So what about the case when it's k plus 1? Well, e of k plus 1 times x. Let's go ahead and distribute inside of this function here. So this is really e of kx plus x. And we just showed that this function e has this nice property that when I have this sum of two numbers inside of the argument of e, that's the same thing as e of the first thing times e of the second thing. That's a very, very formal way to say that. So in particular, why is that cool? Well, I supposed that e of kx, this thing here, has this nice property with that exponent, that k is the exponent. So I'm going to rewrite that here. Finally, I've got something to the kth power times the same thing to the first power. I've got exponent rules for that. I know I just add those together. Again, I can use my exponent rules because these are nice, in this case, positive integers. So conclude that e of nx is equal to e of x, e of nx is equal to, e of x to the nth power. In particular, notice that e of n, in other words, when x is 1, should be equal to e of 1 to the nth power. And what do you know e of 1 is? E of 1 is Euler's number e. So far, what we've got is e of n is equal to Euler's number to the nth power for every natural number. Now remember, I want to show this is true for every rational number, so I've got to do some work with some fractions. Well, e itself is equal to e of 1 by definition. Let's think about some sneaky ways we can write 1. We write it as 1 over n times n, and now I'm just going to apply the rule we just saw, that this n gets to come out as an exponent. And so that looks like e of 1 over n to the nth power. So e is equal to this stuff here, and if you were going to have somebody solve an equation like, 1 is equal to x to the n, you would nth root both sides, and that's exactly what we're going to do. So the nth root of e should be equal to e of 1 over n. Again, that comes from this equality here. So that tells me that e to the 1 over n power is equal to 1 over n. That's pretty cool. So again, I'm trying to convince you, so far, I'm trying to convince you that capital E of n is just e raised to that power of n. And so far, that's true as well when I plug in something like the reciprocal of a natural number. So let me tell you about negative numbers. So if m is a natural number, notice that 1 is e of 0. And 0, I could be sneaky and write that as m minus m. And I'm going to use, again, my property of e here, that I know e has that cool exponent rule that I know and love. I can split that as e of m times e of minus m. So 1 is equal to that stuff there. Why don't I divide by e of m? So that tells me that 1 over e of m is equal to what's left, e of minus m. And then now what do I know? Well, e of m, I convinced myself up here, e of a natural number should be Euler's number raised to that power. So I'm just trying to say that this denominator is really little e to the m is equal to e of minus m. And of course, I've got exponent rules again whenever this is a good rational number, or in this case an integer. E to the minus m is capital E of minus m. So again, I'm trying to convince you that these things match. We're proving that they match. Now let's put it all together. Let's combine all of our results so far. So for any integer z, m and z, goodness gracious, and any natural number n, what do we see? Capital E of m over n. That's the same thing as 1 over n to the nth power. So e of 1 over n to the nth power. And then I know that this is really Euler's number to the 1 over nth power. And this is all to the nth power. And now what can I do? I can use my exponent rules in order to say that you should multiply those exponents. So therefore, we just showed that e of any rational number, which maybe I'll call r now, is the same thing as little e raised to that number.